stuff.
I read this. I was like, this is a foreign language.
Okay, this is not that bad. So this was the homework question about SAT scores. If SAT scores are normally distributed, oh, this is good stuff. And this might help with some calculator stuff. So we'll throw this in for calculator stuff. If SAT scores are normally distributed, this is the picture, with a mean of 1,000, this is SAT scores, and a standard deviation of 200. So the standard deviation is 200. What is the probability that a student has a score of greater than or equal to 1,100? Okay. So where is 1,100 on the curve? Well, we need a z-score for that. So we calculate a z-score. So the observed score at the boundary is the 1,100 we want the student to have, 1,100 or higher. We subtract the mean, that's 1,000. Divide by the standard deviation, that's 200. So this is 100 divided by 200, which is 0.5, which means we are positive half a standard deviation above the mean. So half a standard deviation above the mean is here. That's where 1,100 lies. And you want to know the probability that we scored at least that much. Then you have calculator magic. And I hear you have a cast. That's fabulous. I'm so excited. And the lights are really not helpful. So hopefully that's visible.
Do you want me to close the sheet?
I think it's that light. But I think we can see that, right?
Yeah.
Okay, so that should be what's on the video. Okay, so let me start a new document just so you don't see all this old crazy there. So all of your normal distribution stuff you can find in two different places. If you go to the menu, so I'm going to click on this menu key. I can't show it without the light shining on it wrong. You can either go to 5 probability or 6 statistics. Either one. If we put it here, would that work?
I think so.
I think that'll help. Oh, yep, Kendall solved it. Woohoo, you go, girl. Okay, so probability or statistics, 5 or 6, they both have the distribution menu in them. So you can go to either of those. And number 5 on both lists is called distributions. That's where you need to go. And you have normal PDF, which is useless. Don't ever go there. Normal CDF calculates the area under the curve, which is your probability finder. And inverse normal will take a probability and give you the cut score back. So we want that second one, normal CDF. So we're going to click on 2, and we get this menu. So I want to make sure it kind of matches what's going on with my picture here. My lower bound is this cut score here. And this calculator is super smart in that it will take a z-score or it will take the raw score. I'm going to show you both ways and you can pick which one you want to do. If I do the raw score, my lower bound is 1,100. My upper bound, this shades all the way up to infinity forever and ever and ever. And since you have a CAS calculator, you actually have an infinity key. All the way down here toward the bottom, this pi key, if you click on it, you get this little menu, and infinity is right there. You also can just put in a really big number. Like you can just put in a big string of 9s, like 9 gazillion, 999 billion. That would work too, but this is quicker. So upper bound is infinity because it does go on forever. And the mu is your mean. Well, the mean was 1,000. And standard deviation, that was 500. And when you click on OK, and this tab key right here is your best friend because the tab key is the easiest way to get from one cell to the next. 42.1% of the curve is there. So the probability that a student has greater than or equal to 1,100 is about 0.421 if we round to the nearest hundredth. And I don't know that your professor's picky about rounding. If he is, that they need something. Yeah, that's silly. Yeah, we shouldn't be picky about that because it's just an estimation anyway, the best we can do. Now, I want to show you one more thing. If we go back to that menu, probability, and number 5 is distributions, and normal CDF. I could also do this thing in z-scores. So if I do z-scores, the z-score here was 0.5. So I'm going to put in a 0.5 instead. Upper bound is still infinity, or a really big number. But I'm going to leave the mean 0 and the standard deviation 1 because in z-score world, the middle is 0 and you're counting by 1. And notice that that's already there. It's the default setting, which means it's less work. You can just put the 0.5 and the infinity in and you can click on OK and be done with it. You get the same number. Uh-oh. What did I do? Did I put in something wrong? Shoot. 100 divided by 200 is 0.5, right? What on earth? I have never seen that happen before. Holy cow. 1100 minus 1000 is 100, right? 100 divided by 200 is half, which is a 0.5. Okay. Oh, no. Oh, I put a wrong number here. I put a 200 in for the standard deviation. Standard deviation is 200, not 500. That's my mistake. That one I messed up. Okay, so I'm going to arrow back up to that because here's another neat little trick. You can arrow up and you can select something old that you put in and press enter, and then you can just go back and edit it. That was supposed to be a 200 for the standard deviation. I put in a 500. That's where I screwed it up. So notice you actually do get the same thing both ways. So obviously I'm more likely to mess it up if I don't use a z-score, so I would go with the z-score. I try to train my students to use the z-score instead because professors typically want to see the z-score calculated to kind of back up the rest of the work, and then you don't have as much stuff to type in, so it's really quicker in the long run. So this should have been a 0.309-ish if we round, so I messed that up real good. You can look that up in the z-table, but this is a really handy dandy little tool, and you know, it's just easier to work with than the z-table is. Fun stuff. Okay, number 2, for this hypothetical SAT distribution, what's the probability of a student scoring 910 or lower? Okay, well, same picture. The mean is 1,000. We want to know where 910 is, so let's find a z-score. 910 is the observed score, minus 1,000 is the mean over the standard deviation of 200. That's negative 90. See, I don't even trust myself now. I don't even trust myself to subtract right anymore. 910 minus 1,000 is 90, negative, right? Yes, it is. So this is negative 90 over 200, which is negative 9/20. Well, how about a decimal? Negative 9 divided by 20 is negative 0.45. That's prettier. We'll go with that one. So negative 0.45. So we're a little less than half a standard deviation below the mean. So if one standard deviation below the mean is there, we're about here. And we want to know the probability that we're less than that. So probability that we're down there. So calculator work. Menu. Either probability or statistics. Distributions is number 5. Normal CDF is number 2. Now, my lower bound this time, it goes off to the left forever, so the lower bound is negative infinity. Notice that's the default setting, because anytime you're doing lower bound is the shaded end. That's just going to be handy to already have it there. The upper bound is negative 0.45. I'm going to use a z-score, so then I don't have to change the rest of these numbers. And then I can actually just hit enter a couple times. It'll skip past the rest of that. That's about 32.6%. And I think the rest okay, hold on. What is the probability that a student scoring 910 or lower or 1,000, 1,900 or higher? Well, on number 3, you just add those. So you take the probability from number 2 and the probability from number 1. You're really just adding those two percentages. So add those numbers together. Oh, followed by. No, number 4 you got to multiply. Because if you're going to have a student score 910 or lower followed by a student score by 1,100, you have to take these two probabilities and multiply them because they both have to happen. Ooh, that's kind of ugly probability world. But you just multiply these two numbers, the 0.309 and the 0.326. Probability of a score less than or equal to 910 is 0.326. So add those for part C and multiply those for part D. Ooh, that's fun stuff.
8. Yeah. So.
Okay, so this is from what is this from, Kendall?
It was just a page in the book.
It's some homework page. It was number 8 that she has circled here. It's the one about admissions counselors at Brainy University. I love that they make up problems like my book does. Believe that the freshman class they've just recruited is the brightest yet. They want to test this belief that the freshmen are brighter than the other. Brighter means they're greater than. That's a one direction. You're only going to shade toward the upper end. You want to know of hitting some boundary and bigger. So it is a one-tailed test because you only worry about being bigger. You don't worry about being smaller. What are the null and alternative? So the null is going to be that the freshmen are not brighter than the other classes, and the alternative are not. I know that's chicken scratching. The alternative is going to be that the freshmen are brighter. Because the null is always your status quo. Nothing interesting is going on. They're not better. They're just the same. So we're assuming here that they're the same. And here we're assuming that one group is better or greater than the other. And I don't know if you have to write yours in words or if you have to write them in variables. With your parameters with p's and means, that I don't really know how you would measure that. So I think probably words are the safest thing to do in that case.
Then number 10 and 12.
Researcher believes that family size has increased.
We have 10 student tickets left for the game tonight. First come, first served. 10 tickets for $5 for the game tonight. And we'll be $8 for
Woohoo! Things are falling apart. Okay. So, 10. I think this looks like it's the same page. A researcher believes that family size has increased in the past decade in comparison to the previous decade. That is, people are now having more children than before. What are the null and alternative hypothesis? And the study design is one or two-tailed. Okay, so the null would be that the mean number of children has not changed. No, status quo, nothing interesting has happened. The alternative would be that the mean number of children, it says they're now having more than before. There's no way that's true. Has increased. And because we're worried about getting bigger, not being different, if it has changed, if the wording had been that the mean number of children had changed, that implies it could either be lower or higher. That would be two-tailed. Because this is a one-direction word, this is a one-tailed test that you're going to run. Okay.
Number 12.
Where's
that 12 part?
Assume that each of the following conclusions represents an error in hypothesis testing. Decide whether each of the statements is a type 1 or type 2. So type 1, let's review. In type 1, the null is true, which means nothing interesting is going on, nothing has happened, and you reject it. Which means you say, oh, don't believe it, something's going on. Type 2 is when your null is false, which is the null says nothing's going on. If it's false, it means there's something going on. Something has changed, and you fail to reject. By the way, don't ever accept it. That'll get you in all kinds of trouble. It's kind of like we never declare people at the end of a trial innocent. We declare them guilty or not guilty. You never get enough evidence to actually prove that they're innocent. You just have a lack of evidence to prove that they're guilty. Same deal here. You fail to reject. You never accept it. Accepting the null, big trouble. Don't go there. Based on the data, the null hypothesis is rejected. Assume that each of the following represents an error in hypothesis. I got to reread the question. So if the null hypothesis is rejected, you've done a type 1. So part A of that question, it should be a type 1 because you rejected the null. Because we're assuming that an error was made by looking at the instructions. Okay, there's no significant difference in the quality care between nurses who work 8 and co. So there was no difference found. If we didn't find a difference, we failed to reject. You only reject if you find something interesting going on. If you failed to reject, you did a type 2. There's a significant difference. Okay, if there's a significant difference, you rejected, which means you're in type 1 world. D. The researcher fails to reject. That's type 2.
That's it.
That's it. Okay. Was that okay? So I'm going to turn this off and try to upload these videos, and I hope they're helpful. And I'm so sorry that I forgot to get back to you before. I'm so sorry.